Today we're going to talk about quantum physics, and this will be our subject for quite a while now. In essence, we're going to be working on the equivalent of Newton's laws for a particle's motion, but adapting to the case when we're talking about de Broglie waves, not just ordinary particles that we're used to. So the kinds of Newton's laws that we're going to have to write down are going to be quite a bit different than F equals ma. This actually had an interesting start to it because Schrodinger was giving a lecture on de Broglie's wave hypothesis and how this gave stationary states in the Bohr model. But another physicist listening to his lecture actually made a very interesting comment. He said that such a thing was childish because real waves that we're familiar with from electromagnetism or waves on a string, all have a wave equation. Once Debye said this launched a series of studies for Schrodinger on how to find such a wave equation, or the analog to Newton's laws. For particles of any sort, from Broglie we have that P is h over lambda, or sometimes written as h bar k. We also have that the energy of a particle is h times frequency, or h bar times omega. The second, of course, started out just for photons, but now we've postulated it to be true for all particles. So how do we write down an equation for a wave which just allows us to solve general problems? So all wave equations are built out of some sort of physical law. And one idea would be that this would just express the total energy of a particle. That the total energy is kinetic energy plus potential. Of course, this is non-relativistic. And in fact, if you want a relativistically correct version of quantum mechanics, this would not be a good starting point. You'd have to use our more familiar formula from relativity, which relates the square of energy, the square of momentum, the square of mass. But Schrodinger started out with a non-relativistic expression. In terms of our quantum quantities, this would give us the following expression. So we're looking for some sort of wave equation that will ultimately yield this kind of relationship between omega and k. And we'll also have to keep in mind that the wave function that we're ultimately going to be looking for to satisfy this wave equation has something to do with probability. In classical physics, we often have traveling waves that look something like this. This, of course, describes a wave moving to the right. Such a wave function could describe a traveling electric field, or a displacement on a string, pressure in the air. And a wave equation that might correspond to this would be something like the following. Where these symbols represent the partial derivative. With respect to x. So leaving everything else constant, like time. It's easy to see that this particular sinusoid satisfies that wave equation. The first partial derivative of y with respect to x is just ka cosine x minus omega t. The second partial derivative, we're receiving the first partial derivative with respect to time. Gives me omega minus omega a cosine omega t. So it does seem to be true, for example, that this particular sinusoid also satisfies the wave equation. Written like so. As long as v is omega over k. But this has an interesting feature to it. This only works for traveling waves moving to the right. In other words, some general function f of x minus vt. But if you wanted to describe a traveling wave moving to the left, this would be described by a general function f of x plus vt. It implies that we would need a wave equation that looks something like this. So this is why we resort to second derivatives, because the second derivative will always cancel out that minus sign right there, and so that the wave equation works for both left and right traveling waves. So we can try such a sinusoid for matter waves as well, and see if this would work. Here k is proportional to p. Actually what it is it's p over h bar. We know that second derivatives have to be involved. so we can describe both left and right traveling waves. So we can write down what is d psi squared dx squared. This would equal minus k squared a sine of kx minus omega t. If we're looking at the time derivative, we'll stop at one derivative here. Because one time derivative gives me minus omega a cosine kx minus omega t. We're stopping because we want a relationship something like h bar omega is h bar squared k squared over 2m for a free particle. So we wouldn't expect to have a second time derivative here. So we'd like to write down something that would look like this. But the problem is on this side, this sign. Problem is on this side, I'd have a cosine function, and on this side, I have a sine function. And I don't have sines equal to cosines. So it's in this moment that Schrodinger realizes the complex numbers are involved. And that in fact, the solution for a free particle must look something like this. Where the exponential of this now imaginary number involves both sines and cosines. And this is easy to believe because when I take one time derivative, I just bring down the argument of an exponential by chain rule. When I take two derivatives, I do the same thing again. It's still an exponential. So if complex numbers and exponentials of complex numbers are not very familiar, I suggest you take a look at this short tutorial on complex numbers at this time. And you can verify that the second derivative is just this. And the time derivative is just that. So both derivatives give me back something that's proportional to the original wave function. In other words, the second derivative with respect to x, h is minus p squared over h bar squared times psi. Well, I'm going to rewrite what p squared is. P squared is 2m times e, at least for a free particle. And I'm going to multiply and divide by minus I over h bar. That's all I've done here. The step from here to here is just having a minus I over h bar. Minus I over h bar. In other words, I have something that looks like this. And that's Schrodinger's equation for a free particle. The left side is something like a kinetic energy. At least it will be once I take that second derivative. The right-hand side is something like an h bar omega equals E. More generally, Schrodinger's equation looks like this. So that is, when there's a potential, I should have an equation that has something like kinetic energy plus potential equals total energy for a particle. There are many other differential equations you could come up with. In fact, we'll do some of those on the homework. But this one has the properties that it's linear. That is, it'll be the superposition principle. If two different wave functions are both solutions, then the sum of them will be. And it has the kind of build-up, the kinetic plus potential equals a total energy, so it has some basis in a physical law. And the other thing that's interesting about it is that it clearly points out to us that the wave functions will be complex because there's an imaginary number I right there. So with this, we'll end up trying to develop a more general solutions for quantum mechanics using this basic law.